Our second effect to look at with SN1 reactions is the leaving group. And this is one of the easy ones to look at, because if you recall everything that we said for the leaving group in an SN2 reaction, it's all the same here. So nothing new to talk about in this spot. The better the leaving group, the more reactive the compound will be. So nothing new when it comes to leaving groups. What about the nucleophile? Well, to talk about the nucleophile, we need to look at the mechanism again. So what we want to think about is the fact that our first step is the rate determining step. And so what that means is that the nucleophile is not involved in the rate determining step. Because it's not part of the rate determining step, it has very little effect on the reaction. So this is very much the opposite of what we saw in SN2. In an SN2 reaction, the better the nucleophile was, the better the reaction worked overall. But SN1 is the opposite. In an SN1 reaction, it doesn't matter what the nucleophile is. Regardless of what the nucleophile is, the reaction is still likely to proceed. And again, that's because the nucleophile doesn't add in until after the rate determining step. Once we've done that rate determining step, we have an unstable carbocation which the nucleophile adds to very easily. Our final effect to consider is the solvent. So an SN1 reaction works best with polar protic solvents. So recall that these are things like ethanol or alcohols in general, as well as water. In fact, our first lab in this course is one where you're going to be testing a number of different alkyl halides to see if they can undergo SN1 or SN2 reactions. And one of the ways that we do that lab is we make the conditions such that the conditions in one half of the experiment favor one reaction, whereas the other half they favor the other reaction. And so what we do in that experiment is in the first part we use acetone. Acetone is polar but aprotic, and so it favors SN2. Whereas ethanol is also polar but is protic and will therefore favor SN1. So why is it that polar protic solvents favor SN1? So polar protic solvents are able to do a good job of solvating cations. As a result, in an SN1 reaction, it's able to stabilize the cation intermediates. And as we've talked about before, if you stabilize the intermediate, you lower the transition state energy, which as a result lowers the activation energy. But if this is our cation, and let's say the reaction was taking place in water, the lone pair on water can coordinate to this carbocation, which helps to stabilize it. So what do we use as solvents for SN1? Well, water is very good at promoting ionization. But what's the drawback of water? Well, a lot of organic compounds are not soluble. Alcohols, while not as good as promoting ionization, they are able to do it, but they have the much more important benefit of organic compounds being soluble in many alcohols. So this is the best overall choice. The other type of species that could be a polar protic solvent are carboxylic acids. The issue with them, though, is in some cases they can be too acidic, and that acidic proton could end up reacting with the compound. So I want to show you now an example of an SN1 reaction, one that we could run across outside the lab. And that has to do with sodium nitrite. So, do we know what sodium nitrite is used for? So, sodium nitrite is very commonly used to processed meats as a preservative. And over the years that they've had to decrease the amount of sodium nitrite that you're allowed to use in food. Why is that? Well, if you have an amine present, and we certainly have plenty of those present biologically, an amine is able to react with sodium nitrite to form this rather strange looking species. This is known as a nitrosamine. If you take a nitrosamine and add either acid or heat to it, you'll get what's known as a diazonium ion. And a diazonium ion is something we're going to see again in this course. Diazonium ions are extremely useful in organic chemistry because N2 is about as good of a leaving group as you can have. Why do we say that? Well, if you want something to be a good leaving group, you want it to be stable. Well, when this bond breaks and this leaves, we get a carbocation plus nitrogen gas. And we don't have many things that are more stable than nitrogen gas. Getting nitrogen gas to react is extremely difficult. In fact, so difficult that when you do research in organic chemistry, many of the reactions that you run have to be run in an inert atmosphere. And that's because things like water and oxygen that are present in the air can react with many intermediates or organic reagents and ruin your reaction. So you need an inert atmosphere to run the reaction. And there's two very common gases that we use for that. One is argon, which is a member of the noble gases we know reacts hardly at all. And the other one that we use is nitrogen. Now, argon works a little bit better. It's heavier. And so if you have to open your reaction flask up to add a reagent, which is something you generally do from time to time, the argon doesn't get displaced by air as easily. But the nitrogen ends up being a lot cheaper. But again, the main message here is that nitrogen gas has a reactivity similar to that of one of the noble gases. Very, very difficult to get it to do anything. And so it's a completely stable leaving group, but it has a second feature that makes it even better. So as I said in a previous lecture, we should be drawing most of our reactions now as equilibrium situations, because most steps within a mechanism are reversible. This step isn't. Why not? Well, nitrogen is a gas. As soon as it leaves as nitrogen gas, it goes away. It evaporates. And so even if it wanted to react and be reversible, it couldn't, because it's not in the reaction solution anymore. So the final step is that a nucleophile then adds to the carbocation to give us our product. And so you can see the last two steps of what's happening here is our SN1 mechanism. Leaving group leaves, and then after the nucleophile leaves, then after the leaving group leaves, then the nucleophile comes in to form the new bond. And the problem with this reaction is it depends on what nucleophile adds in. So for certain nucleophiles, this is what can result in the carcinogenic nature or actual cell death. So because of that, there are limitations on the amount of sodium nitrite that you can use to preserve meats. All right, so let's just summarize before we go and do some practice. What favors SN1 and what favors SN2? So SN1 wants a protic solvent, whereas SN2 wants an aprotic solvent. For leaving group, they're the same. Both are favored by good leaving groups. Nucleophiles, an SN2 wants a good nucleophile. For SN1, it doesn't matter. And for substitution, for SN1, more substitution is better. And for SN2, less substitution is better. So now you should get out our first in-class exercise for Organic 2, which you'll see is labeled as in-class exercise number 1, just labeled SN1 and SN2, and work through some of those examples.